Good morning. So this is the 18th lesson of algorithmic design. Last time we introduced algorithms on graphs, and in particular we introduced BFS, so breadth first search, which is a way to browse a graph and discover distances from the source we provide at the beginning of the computation. So we understand the intuition of the breadth first search, and we saw the pseudocode. But at the moment we are still lacking of a proof of correctness. So we understood that the complexity of the pseudocode is big O of cardinality of V plus cardinality of E, where V is the set of nodes in the graph and E is the set of edges in the graph. So what about the correctness? So let's try to prove the correctness of BFS, first of all by proving a small lemma, which is quite useful. So the lemma we want to prove at the very beginning is the following one. So lemma, let Q V1 Vn be the Q of BFS at some point of the computation. So Q is the Q we are using to search our graph. Then we can say then it holds that vi distance is smaller or equal than vi plus 1 distance, and for all I belonging to let me see, 1 and minus 1. So if you remember, before placing an element inside the queue, we are updating, let's say, its distance, and this update is performed once per node. So once you have set the property D of a node, you never change it. Well, of course, you set it during the initialization, but apart from the initialization, when you change the property D of a node inside the while loop, that node doesn't change anymore. And the point is that that property is set exactly when the node becomes gray, but then once it becomes gray, it never change anymore. Why? Because after visiting all its after adding to the queue all its white neighbors, that node becomes black and then removed from the queue, and so it cannot enter anymore in the queue itself. And so this is the property number one, and the second property is and the second property is that v1 dot d plus 1 is for sure greater or equal than n dot d. Okay, so this small lemma tells us that at any point of the computation, at any instant of the computation, the Q contains all the nodes having more or less the same value for the property D. And in particular, they are non-decreasing. So the first element for sure is smaller or equal than the second one. The second smaller or equal than the third one, and so on and so forward. And the distance, the difference between the property D in the last node, which is greater or equal than the property D of the first node, and the property D of first node is smaller than 1. So the difference between V and V and D and V1D is for sure smaller than 1. Okay, so how can we prove it? And the proof is quite simple, because we can prove it by induction on the number of iteration of the while loop. So by induction on the number of iteration of the while loop. Okay, so at the very beginning, so when base case iteration 0, so at the very beginning, so when the iteration is 0, Q exclusively contain the source, and so the property holds. Okay, or better, rather than property, the thesis holds. Let me delete also this one. Induction step, inductive step. So let us assume that this is all for but the property hold rather than the thesis in this case. Holds before the ith iteration. And let's see what's going on during the ith iteration. So during the ith iteration, so we have a Q done in this way. This is B1, this is Bn, and the I d is smaller or equal than the I plus 1 dot d, and for all I belonging to 1 and minus 1, of course. And as said before, we know that the n dot d is more or equal than well, let me move all this stuff below. More or equal than v1 plus 1. Okay, this is what we know. So during the ith iteration, the first thing we do is to extract the element at the beginning of the queue, so the first element in the queue, which is v1. So so we extract v1, and then for all the neighbors of v1 which are white, we place them on the at the end of the queue. Okay, so let v1 let me say 1 1 v1 m be the white neighbor of v1 neighbors of v1 white neighbors of v1. Okay, so after the ith iteration, q will be v2 vn, but let me again move this stuff below. v1 1 v1 n. Okay, now since this property holds, since this property holds, okay, we are guaranteed that all the white neighbor we added at the end of the queue will be greater than this one, than the n. Why? Well, the property d of these nodes for sure will be greater or equal than the property of the n. Why? Because of this property. So we know that v1 plus 1, sorry, not v1 but plus 1, but the property d of v1 v1 plus 1 is greater or equal than the property d of the n. Now the property d of the white neighbor of v1 is exactly v1, the property d of v1 plus 1. Okay, so this stuff tells us that v1j is which is equal to, well, v1jd, which is equal to v1 d plus 1, because of the code, of course, is greater or equal than the n dot d. Okay, But because of the other property, because of this property, we know that v and d is greater or equal than di dot d. And this holds for all j belonging to 1m, where j is the index of the white neighbor of v1. Okay, and so you can see here the white neighbor of v1 goes from 1 to m, and j goes from 1 to m, and for all I belonging to 2, which is the, this is a 2. Let me rewrite it in a better way. So this is a 2, and from 2, which is which is what is now the first element in the queue, up to, of course, n. Okay. So we were able to prove that basically for all I going to, well, we're basically able to prove that for, let me rename basically all the nodes in the queue, and so let me rename them as I prime, vn minus 1 prime, vn prime, and so on and so forward. This is n plus n minus 1 prime. So what we were able to prove, I just rename all the nodes just to have them have their indexes subsequent. So we just proved that for all I going from 1 up to n plus m, I prime dot d is smaller or equal than the I plus 1 prime dot d. Okay, so now we are left to prove what? We are now left to prove that v2 d plus 1 is greater or equal than v1 m dot d, of course, but this is clear. Why? Because v1 m dot d is equal to v1 d plus 1 because of the code, of course, and since we know it turns out that this can be this is equivalent if only if v2d is greater or equal than v1 d. Okay, but this property holds because of our assumption. So at some point we assumed this condition, and this condition is useful to prove this condition. Okay, so this is enough to prove our lemma. So we now know that, let me repeat, we now know that that this lemma holds. So at any point of our computation, the queue is done by nodes whose property D is such that the first element in the queue has a property D which is smaller or equal than the second one, than the third one, and so on and so forward. And moreover, the difference between the property D of the last one and the first one, and of course of all the elements in the middle, is at most 1. Okay. So why is useful why is useful this property to prove the correctness of our pseudocode? Well, it's useful because we exploit it in proving the following theorem. So let delta S V be the distance, so the distance which is basically the length of the shortest path between S and B. Okay. The distance, of course, I missed to say which distance. So this is the distance from S to B, which is the length of the shortest path between S and B, of course. So after BFS, three property holds. The first one is that VD is different from infinity if and only if V is reachable from from S. Property number 2, if the property T is different from infinity, then V of D is equal to delta of SB. And the property number 3, so the shortest path from S to V and so it's concluded by the edge let me see, V press V. So this is an edge, and I'm saying the shortest path from S to V is concluded by the edge moving from the node which is the predecessor of V to V. Okay, so how can we prove all this stuff? well, let me do it. Well, as far as the first step may concern, it's quite easy. We can prove it by contradiction. As you may remember, the property D becomes equivalent to infinity as soon as we set the color of V to white, and as soon as it becomes gray, the property, so as soon as the node becomes gray, the property D changes, so it's decreased to an integer value. So saying that V is not equal to infinity if and only if V is reachable from S, is just as saying that it is equal to 0 if it is not reachable. If and only if it's not reachable. Okay. So let's assume by contradiction that V is not reachable, so it's then white, and at the end of BFS. Since it's reachable by contradiction, since it's reachable from S, there should be a path from from S to V. And since BFS has ended in our assumption, so there shouldn't be any gray nodes. So all the nodes in the graph should be either black or white. And this, of course, also along all the nodes on the path from S to V. So let's take so what? Since BFS ended, all the nodes in G must be either black different from infinity, or white D equal to infinity, because okay, so this holds also for the path for all the nodes on the path on the paths from S to V, of course. Okay, so let take one single path. So let take W, which is the last black node on one of the path from S to V. So let W be the last node, black node, sorry, last black node from on one of these paths. Okay. Now, since W is the last black node on this path and should be the last node because we know that we assume that V has a distance equal to infinity even though there is a path from S to V. So if it is equal to infinity, V should be white. So for sure S at the beginning of computation becomes gray, and so to conclude the computation of BFS should be became black. So there should be for sure a W along the path from S to V black, the last node which is black, and so let's assume this is W, and now since this is the last node and since it is black, all its neighbors should be either gray or black, but we concluded our BFS, so all the neighborhood of W should be black. This of course includes the neighbor of W, which belongs to the path from S to V. So however, since W is black, all the nodes reachable from it crossing an edge must be non-white. Okay. And including, so let me including that on the path from S to V, right? Okay. So this is a contradiction. So because we have a further nodes on the path subsequent to W, which shouldn't be black, and since it is not black, it should be either gray or black. Should be white, should be either gray or black. But because BFS ended, it should be black. Okay. So this is a contradiction. And this means that for sure, if V is reachable from S, then the distance from the value D, the property D of V should be different from 0. Okay, you can do it on the other way around, but basically the reasoning is always the same. So if D is different from 0, then the node should be black, and to be black there should be a node coming along the path from S, and then this proves that there exists of course a path from S to V. Okay. Now what about the distance? Well, what about property number 2? Well, property number 2, so the point number 2 it comes from lemma. Okay, since at each iteration we increase by one well, it comes from lemma plus induction on the length of the shortest path. So let's assume we have already computed that the property holds for all the shortest path smaller than a certain value, and we want to prove it for the shortest path greater than that smaller value. Then we can basically prove it directly by using the lemma. Okay, and this is it. So what about the third point? Well, the third point is a consequence of point 1 and point 2. So if there is a shortest path, the shortest path should end with this edge, because to compute d, which is the value of the shortest path, we pass through the predecessor. Okay, and again by induction on the length of the shortest path, it is obvious that the shortest path from S to the predecessor of D plus this edge is basically the shortest path to D. And this is due again from to the lemma, because we always extract the shortest path. So the node whose distance from S is the shortest one. Okay, and this is it. So this is a proof of what we saw the last time, and so we may. Okay, this is the complexity, and let me see here. Okay, let me see, I have a question. So we are saying Q is either contain all the nodes that have the same distance from the source, or contain a mix of nodes that are one step away from the source and one step away from the source. So someone is asking whether Q either contain all the nodes that have the same distance from the source, or contains a mix of nodes that are n steps away from the source and plus 1 steps away from the source. Yes, but they are also sorted according to the steps from the source. Okay, so the first element in the queue is the nearest to the source, actually. Okay, with respect to the other one in the queue. So the queue contains all the gray nodes, and the first one in the queue, which is the node which has been inserted first with respect to the other ones, is the nearest to the source. Okay, and this is the complexity as we saw, and this is the lemma and the theorem as we saw. So we can move on to the next way to browse a graph. So we saw breadth first search, and we understood that by using breadth BFS we are able to compute the distance of a node from a source, and we are also able to compute the BFS tree, which is the tree of the shortest path from the source along to all the reachable nodes, of course, towards all the reachable nodes. Now we have another way to browse a graph, which is depth first search, and and let's have a look at it. So different from what we saw from BFS, which proceed by enlarging in some sense a wave. BFS and of course does not reach the unreachable nodes. BFS reach all the nodes of the graph. Okay. So in the case of BFS, there may be nodes which are not reachable, so they are not reached by BFS visit. While in the case of DFS, we reach all the nodes of the graph. And the idea is to repeat a kind of iteration by selecting non-visited node at the source of the search. Okay, so we select a node from the graph. We try to expand as much as it is possible all the path from leaving that node. Okay, by adding non-visited node, and then at some point it might be the case that no more nodes are reachable because for instance, the graph is not connected, or you selected some nodes which are not reachable to reach other nodes, which however can reach the first one. And so the idea is to repeat the process, to repeat the extraction of non-visited node, and perform everything we did before with a new node. Okay. And we go on. So what the DFS produce is not really a tree, is a forest. Why? Because as I said before, it may be the case that the graph is not connected. Okay, and so that's why we are not returning a single tree, but a set of trees, which is called forest usually. Now, another interesting thing, different thing with respect to the BFS visit is that DFS labels all the nodes by using two values, which are not the distance from the source, but they are discovery time and finishing time. And we will see later on why they are useful. Okay, so let's have an example. Here we can see the graph we saw on BFS. This is exactly one we saw on the BFS example. As you see at the beginning of the computation, we have all the nodes are labeled by two values, which are unknown at the beginning. Okay, or better, not set. And as in BFS, we have three kind of nodes: white, gray, and black. So the white nodes are the nodes that have not been discovered yet, as in BFS. The gray node has been discovered but not finished yet, and let me see, and the black nodes have been finished. Okay. So as I said before, the first step in DFS is to select one of the undiscovered nodes, so one of the white nodes, and in doing it we set discovery time. So at the beginning of computation, discovery time is 1, and so in our example, by discovering this node as first node, and this is just a case, I mean, it could be this one, it could be this one, it could be this one, it's not really relevant which is the one we are discovering first one as the first undiscovered node. However, in discovering it, we gray color it and we set its discovery time to 1, because this is the first step of our algorithm. Okay. Then we move to one of its neighbors for instance, this one, I mean, again, I choose this one, but it could be this one, doesn't matter. It's not really relevant. And in discovering it, as you may see, we set its discovery time to 2. Why? Because this is the second step of our algorithm. But we are still leaving undefined the finishing time. And the same is for this node. Okay, so once this is done, we try to enlarge the path by selecting another node following the last one. So in the case of BFS, we basically included all the neighbor of the first node inside Q. In this case, we are simply trying to enlarge the path by selecting one of its possible neighbor. Again, as we did for this node, for instance, and so we may select this one. Again, I selected this one, but it could be this one, doesn't change. Okay? And again, since this is discovered as step number 3, the discovery time is set to 3, but the finishing time is still left undefined. So we go on, as you may see here, and we go on by increasing the discovery time and gray coloring the new node in the path. Now we reach this point, so this node, which of course has 2 edges leaving it. However, all the nodes reachable by crossing these 2 edges are non-white nodes. So this path cannot be enlarged anymore by adding a new undiscovered node. And so this means that this node can become now black. And I can also define its finishing time, meaning that all the undiscovered nodes reachable from this node has been reached. Okay. So this node has been discovered at time 4, and finished at time 5, because I cannot move anymore from it along a white node. Okay, so once I finish this node, I should backtrack into this one and try to extend the path up to this point, going to a new undiscovered node, and this can be done by crossing this edge and reaching this node. Okay, so now what's the discovery time of this node? Well, the discovery time on this node is 6. Why? Because as we observed here, the finishing time was 5 for the black node, from this black node, and then the next step is 6, of course. Okay, and again, from this node I cannot reach any white node, so I end up in coloring it and defining its final time, which is 7. And we go on. Now from this node I cannot reach any white node, so this node has no more white neighbors, and then it becomes black, and I set up its finishing time. I can backtrack into this node, try to extend this path, the path from this node up to this one, and this is the result, and this is the result, and so on and so forward, and here. Okay, so this is the result of the first let's say, iteration of expanding all the possible branches, all the possible paths from this node. I mean, again, I selected this node by chances. It's not a proper selection. It's not a selection done by user, but a selection done by the algorithm itself. We decide to somehow to pick up this node in place of this one. It doesn't change anything. Now DFS hasn't finished its visit. Why? Because we are still left with this node undiscovered. So the next step performed by DFS is to select another undiscovered node, and the last one is this one, and repeat the step we saw up to this point. So the first step is to discover it. The next step is to finish it, simply because it's not possible to reach any other nodes from it. Okay, and this is a simple example of the first visit. Now, how can we encode how can we encode by pseudocode all these behaviors? Well, let me move to the whiteboard to write the where can I find it? Here. Okay, let me move to the whiteboard to write the pseudocode of this algorithm. And the pseudocode is just one single function. Well, two functions actually. The first one, we call it DFS, is the main function, let's say DFS, and as opposed to VFS takes one single parameter, which is the graph on which we want to operate, which we want to browse, and for so for all nodes in GV, what we should do, well, first of all, of course, we need to color we need to color it, color white, and we need to set the predecessor, as we did for BFS, to null. Okay, and this is all. So as you see here, I'm not setting, as we did for BFS, the property D and the property F, which will be the discovery time and the finishing time. And the motivation is that for sure DFS will visit all the nodes in the graph, so it's going to set all their properties. While in BFS, we are not guaranteed that all the nodes in the graph will be visited, because the graph itself could be not connected, or there may be some nodes which are not reachable from the node we selected as starting point. And then in that case, to know that they are not reachable, or better, to compute the distance, the proper distance from the source, we need to set the property D to infinity. But as I already said, in this case we are going to visit all the nodes in the graph itself, so we are not required to set in the initialization part any of the two property we are going to label all the nodes. Okay, So once we have initialized in some sense the data structure, we are required to declare a new variable time, which is a variable, the variable which takes the elapsing time of our procedure, in some sense count how many steps we had performed from the beginning of the computation. Now, for all the nodes, again, in GDV, we should check whether the node is white. Okay, and if this is the case, we basically call a new function, a new procedure. We will see in a while a new function which we will call it DFS visit. Moving from operating on Z and moving from V itself. And this procedure that we are going to see in a while, we return a final time. So the time required to we are missing actually we are missing one parameter here. We have to pass time, of course, and the returning time of this procedure will be the final step performed by the procedure itself. So once we have done this will be an if, and here we will have an end for and an end death. Okay, so this is the main procedure. This is the main procedure of DFS, which is I mean, quite easy to understand. The first part, so this part is initialization. Or better to no, probably it was correct before. And while the remaining part, so this part is the part which takes care of selecting new nodes which has been discovered yet, as we saw in the previous example. So the last node we visited is not connected to the in any way to the first selected node, and so this is why we are repeating this for loop. Okay, so this is the main loop. Okay, now let's try to write the FS visit then. And again, this is quite easy. Oh, I deleted it. It should be time. So this is DFS visit GD time. So the first thing we need to do in the FS visit is to increase time Why? Because we are performing one step. Since we are calling DFS visit on V, for sure V is white. Okay, so before coloring it gray, we need and set its discovery time. We need to increase time by 1. Now we can set its discovery time. So VD, which is again discovery time and not distance, is set to time. And of course the color should be set to gray. Now once this is done, we need to perform a for loop for u in G adjacency of V. So for all the neighbors of V, we need to check whether the neighbor itself is white. So if it is white, we may try to enlarge the path from V, and this is done by setting the predecessor of U to V. So from V I'm moving to U, okay, and then the predecessor of U for sure would be V, and then what? And then I need to call again the DFS visit. So time DFS visit G, sorry, not V but U, and time. Okay, so here I'm saying, look, I'm discovering new node V, I gray color it, I updated the discovery time. Now I can try to enlarge all the path moving from it, and to do it I need to search among all its neighbors by I need to search all the white node among its neighbor, and if a node is white, for sure the predecessor of that node would be the one I was dealing during this call, and I need to keep going in visiting that node. Okay, and after that I of course need to conclude this if, I need to conclude this for. And 4, and two things are missing here. Well, one thing is missing actually, and once I perform this visit along all the neighbors so I stretch as much as I can all the path moving from V. For sure I visited, I conclude all its successor in some sense. They are all black. Nothing more can be done from this node because all its successor for sure have become different from white. So if this is the case, I can say that this node is concluded, has been finished. But before saying that it is finished, I need to increase by 1 the time. So first of all, I need to increase the time by 1. and then after that I can say that D, which is the node I was dealing in this call, D F is equal to time. Okay, once this is done, I must return time. And that. And this is all. Now let's try to, if it is clear, please let me know if you was able to follow me. And let's try to figure out the complexity of this code. Well, first of all, let's try to focus on the FS visit. Well, the complexity of the if block, well, of the for block, of course, is theta of 1. Well, no, this is not true. Sorry, this is not true. So let me do another stuff. So every time I'm calling the FS visit, I'm grain coloring the node. So for sure, I can, since I'm calling the FS visit and most only when the node I'm calling which is passed as parameter is white, the number of time I'm calling the FS visit is at most equivalent to the number of nodes we have in the graph. So the number of calls are, well, not at most, but for sure are length of V. Remember, the FS visit is also called here, and we are going to call it every time V is different from Y. Okay, and every time I'm calling it, the node I'm calling the FS visit, so the second parameter becomes gray. So the number of calls of the FS visit are exactly the number of nodes on the graph, and this is because the only way to change the color from oh yeah, we are missing another things actually. V is this color becomes black, of course. So every time we the only way to change the color of a node is to call the FS visit. So the number of calls of the FS visit should be equal to V, and in particular every node in the graph would be considered as parameter once for the FS visit. Now, what about this the number of iteration of this for loop? So the number of iteration of this for loop iteration are G. So the number of iterations of this for loop are basically the cardinality of the neighborhood of V. But since we are calling the FS visit on all the nodes of the graph once for sure, because at the beginning of the computation all the nodes were white, and at the end of the computation all the nodes should be non-white because of this for loop. For sure the total number of iteration of this for loop globally will be so globally, let me number of iteration globally are cardinality of E. Okay, so I repeat it. For each call, the number of iteration of this for loop is the neighbor of V, where V is the parameter we are passing to DFS visit. But globally, since DFS visit is called on every single node of our graph, the number of iteration globally of this for loop is E, the cardinality of E, so the number of edges in the graph. Okay, so the complexity of the FS on a graph VE will be theta of cardinality of V plus cardinality of E. Please notice that while in the case of BFS we have a big O, here we have a theta, and this is due to the fact that for sure we are going to visit all the nodes in the graph. And because we are visiting all the nodes in the graph, we are also visiting all the edges in the graph. And this is all. Okay. This is another way to browse the graph itself. Now we are left with we are missing, let's say better, we are missing the proof of correctness of this on this algorithm. Well, the correctness is due to, let me go to again to the previous slides, to the previous slide, is due to this main loop. So the main loop guarantees that all the nodes in the graph will be visited. Now we have two interesting property that should be proved on this algorithm, and the properties will be useful for the next topic. So let me mention them. The first one is the following one. So is a theorem called also parenthesis theorem. Also known as parenthesis theorem, which says that we are missing, well actually I missed to well no, I'll tell you later on. So for any node, for any pair of nodes, and let me call them V and U belonging to V, either, so we have three possible cases, either one, U belong UD, so the discovery of U, so the time going from the discovery of U and the finishing of U intersect with the time going from the discovery of V and the finishing of D, okay, is empty. And so either this, so if this condition holds, then neither U is a descendant of V nor V of U. Okay, so by descendant I mean in the descendant in the forest. Okay, so by performing DFS we build up a forest, which is the forest of the trees we build up in performing the DFS visit. When I say that U is not a descendant of V, I mean that U has not been reached moving along V. Okay, and so by looking at discovery time and finishing time of U and V, you may guess whether U is a descendant of V or V is a descendant of U. And in particular, for sure, if the discovery time, so the time going from the discovery time of U and finishing time of U does not intersect the time between the discovery time of V and the finishing time of V, then for sure we did not discover U moving along V, and we did not discover V moving along U. Okay. Moreover, if otherwise U dot V dot F, so the time, if the discovery time and the time between the discovery time and finishing time of U is included in the time between the discovery time of V and the finishing time of V, then what we can say, well, we can say and U is a descendant of V. Okay, and what about the remaining case? So so it could be the case that V and so the time between the discovery time of D and the discovery time of well, no, this is not the case, sorry, this is the case. So the time between the discovery time of V and the finishing time of V is a proper subset of the time between the discovery time of U and the finishing time of U. Then for sure, as you may imagine, V is descendant of U. Okay, so this is the theorem, the parenthesis theorem, and this basically says what we just saw. So to discover whether we were able to reach V moving along U, we simply have to look at their discovering and finishing time. And moreover, this theorem also tells us it is not possible to have an intersection between discovering and finishing time of two nodes, of course. An intersection which is not a complete inclusion. Okay, so this is it. This is the theorem. How can we prove it? Well, it's almost straightforward. Is almost straightforward. I mean, I want to left you this proof as an homework, but let me mention, because we are almost out of time, so let me mention the other important result about DFS visit, and we will see in the next lesson why so important. the next result about DFS is called wide path theorem. And the wide path theorem tells us the following thing: for any pair of nodes V and U belonging to the nodes of G, of course, U is a descendant of V if and only if at time so the center of V at time VD minus 1 there is a wide path. So by wide path I mean a path containing exclusively wide nodes, a wide path from V to U. Okay, this is, I mean, quite easy to see. If there is a wide path, then by repeating all the codes to the DFS visit, I end up in moving from V up to U. And so U is a descendant of V. And this is all. Okay? So again, why these two properties are so useful, we will see them during the probably next lesson, or maybe the lesson on Tuesday. Anyway, for sure they will be quite useful in improving the correctness of another algorithm we will see, which is about strongly connect component, but we haven't yet introduced the notion of strongly connect component, so I don't want to spoil anymore the next lessons. So I hope you enjoyed this lesson and you understand it. If this is not the case, please let me know what's going on. Oh, I see another question here. Theta of V comes from initialization, right? So someone with your colleague is asking about the code of DFS, I guess, and wants to know why the complexity is theta of V plus E. Well, the complexity is theta of V is at least theta of V because of two reasons. The first one is, of course, the initialization, but of course we also have the main loop, which is repeated along all the nodes of V, despite not all the nodes will be white, despite the fact that all the nodes wouldn't be white. But still, the if condition is tested, the condition of the if statement is tested at exactly cardinality of V, so times. So the theta of V comes also from the main loops. And the third reason why we are dealing with that theta of V complexity is because at the end of our visit, we will deal with, so all the nodes will be different will be black nodes, and well, non-white nodes, and this is You can see it because of this for loop and this condition, and so the number of calls of the FS visit for sure will be exactly the number of nodes in the graph, because the only way to change the color from white to gray and then black is to call the FS on the nodes you want to change the color. Okay, and since at the end we don't want to have any white node on the graph, for sure we are going to call DFS visit at least, but in any case at most, because of the condition on the conditional statement, both on the main loop and on this for loop, exactly cardinality of the times. So you mean more, so your colleague is asking whether in this point should be empty. Oh yes, of course. So this shouldn't be different from 0. This should be from empty set should be equal to empty set. You're right. Okay. And that's all. So again, I hope you enjoyed the lesson, and please let me know what's going on, if you can understand, if you can follow me, and if this is not the case, I'll try to explain everything in a different way. We will see a new algorithm on graph on Monday. In particular, we will investigate something called topological sort, which is quite useful in implementing, let's say, cakes. Okay, so see you on Monday, and enjoy the weekend then. Bye.